Hello everyone, my name is Joe Scorsone, channel is called Ethernet Link, and today we have episode 17 of the Quant Finance Admin to Code. Late upload, I know, but I felt terrible last night. I had my last final today, so I'm feeling retired, honestly. I feel like I have a Social Security check company in the mail. I know I don't, but that's how I feel right now. I am checked out. I am ready for this break. I'm ready to provide you guys a lot of content over the break and to just write a lot of music and just really relax. I've been trying to turn my personal X into more of just like kind of like a journal, almost just like whatever thoughts I have, just kind of put it out there. And whenever I write music, I can actually play it, I'll post a video of myself playing that on my X. So if you guys like metal music and stuff like that, just chat about it there. So yeah, I am so happy that this semester is, and I feel like people can just hear it in my voice. I'm so relieved. But yeah, this is my business X. The personal one will be in the description. This is my business X. All the updates will be on there, and you guys can know when I got hop on spaces with everybody else and take trades. Hit a good one on Zoom this morning. It was called out live, and here we have the algorithm flux algo. I used it this morning, helped me get my entry. So you guys could get more details about this from the description and subscribe to it if you think it would help your trading. So I'll have to switch that first. No. Yes, and make sure I get this up. Perfect. So our task is to do a PCA analysis on the yield curve to determine which components drive the move the most. Also project onto the principal components and blah blah blah. And so to get the links for all the CSVs that I'm using, you could just go to the St. Louis Fed website. They're all totally free. There'll just be a big blue button that says download, and then just make sure you download the CSV, and I just put it in a different directory that just says bond yields, just like that. So yeah, with that all done, let's go into the code, what we're actually trying to do here. So to get a different data frame for each bond yield, and I'm saying observation date because that's what the column is in the CSV. So that'll be our index. Put them all together and then drop the missing values, and we could just say in place and drop them based on time. Now we have to normalize it, so that way we get rid of a lot of noise and we can accurately model it with PCA. So we have to normalize the data, get the mean to be 0, so we can just subtract yields minus their mean over the standard deviation. Now we have to get a covariance matrix, and so this is where the linear algebra comes in. This is all linear algebra. Yes, I know. I just had a class on this. I mentioned that in my video about Garch models, and yeah, maybe at some point I post the paper. Maybe I add more detail to it because I'm actually going to just be doing it for me, and then I post something about it. Regardless, we need a covariance matrix of the normalized yields, and row variables is false. We're using columns, right? We're using columns in linear algebra. It is very contextual if you're using columns or rows in your operations. So yeah, a higher value in the covariance matrix will indicate that there's a better relationship between two or more of the components, or two or more of the things, two or more of the variables, whatever. Then we can get the eigenvalues and the eigenvectors from that covariance matrix. So the eigenvalues will determine, or the higher the eigenvalue, the higher the variance of whatever value that we're looking at, and the eigenvector is the direction of that variance. So then we could sort them by biggest to smallest. And so then we're going to pick the top two components. We're going to get the top eigenvalues, and then we're going to project the yields onto those top eigenvectors. We're just going to do that by a dot product. So if you guys don't know what dot product is, this is in machine learning too, so I'll just super quickly explain what a dot product is. So if I have a vector 1, 2, and then I have 3, 4, that's a terrible 4. And then I have 3, 4, and I want to dot product them. That'll just be 1 times 3 plus 2 times, I'll give you a better dot there, 2 times 4. So that'll be 3 plus 8 equals 11 is our dot product. Dot product, this looks like a smiley face. Dot product gives you a number, not a vector. So that's what dot product is. Yeah, so we're just going to do that for every every vector that we have, or for the top eigenvectors that we have, normalized yields dot the top eigenvectors. So then we're going to plot the explained variance ratio is the just move that R, the eigenvalues over the sum of all the eigenvalues, and that'll actually give us the explained variance of it. We're going to get into all that. It'll be a lot easier to understand when we actually see the plots. So let's get those up here. If we just run the script, it's going to go onto my other screen. So then that's our second graph. This is our first one. So now our x-axis is the explained, or x-axis, modon, is the component that we're looking at. The y-axis is the explained variance ratio. So a high value for, well, we can see here that a high value for PC1, only 2% of the data, 2.3, less than 2.3% of the data is actually explained by something else. It's all explained by the first component. And so what that could mean, excuse me, is that one or more of the underlying factors are influencing all the bond yields, right? So they're all pretty much moving cohesively. And so this could be things like monetary policy and inflation expectations, and that all makes sense. It's all literally what's going on. So it is explained in the math as well. So yeah, PC2 might explain something like slope. So how vertical are yields, right? And PC3 would explain something like curvature. So kind of in the middle of the yields. That doesn't really happen that much because, you know, yields pretty much go up and go up a little bit, right? They should never really go up and then go down, but, you know, things happen sometimes. But this is saying that more often than not, they're all moving in tandem, which leaves out a little bit of the story because the yield curve has been inverted a little bit, but, you know, nothing's perfect. So now, in our second graph, for our PCA analysis, this is component 1 on the bottom, or on the x-axis. On the y-axis is component 2. And you'll notice that this actually does explain the fact that we had an inverted yield curve quite nicely because, you know, 0. So if we have points clustered together, kind of like right here, maybe a little bit over here, down here, this suggests periods where bond yields were similar, right? This doesn't really have an aspect of time to it, but it does suggest to us a point in time where the bond yields across the curve were similar. Outliers like this guy, even this guy up here, a few of them down here, especially this dude, that explains points in times where they were very different. And so then the direction of the spread indicates how one component changes relates to the other component changes. So when PC1 is increasing, right, when PC1 is increasing, things tend to spread out. Things tend to spread out on the y-axis, and when the y-axis increases, PC1 tends to not really have a difference. But we could definitely see that when PC1 is increasing, right? This is what explains most of it. When PC1 is increasing, then our outliers tend to spread out a little bit. Not our outliers, just our points in general. And there's not really much of anything when the principal component is neutral, right? So yeah, you've just successfully done a PCA analysis on the yield curve. I hope you guys enjoyed this video. Hope you guys are enjoying the Advent of Code series. It's been fun for me to make. All done with my semester now. I just want to tell everybody. But so the videos should have a bit more detail in them now. It should be a little bit cooler. I encourage you to dive more into PCA more. It's pretty cool. It's pretty useful, and if it's a good thing to understand because those eigenvalues, like Garch models, also use eigenvalues. Anything where you have to pretty much see what is explaining most of this data, you could default to eigenvalues pretty dang often and have a great model, right? Not even just a good one. The eigenvalues and eigenvectors, they're killer, right? They're pretty great. But yeah, I encourage you guys to go break some stuff, to go copy some code, break some code, steal some code. Maybe not that. Go get as much code as you can in an ethical way and break it, improve it, make it cool, make it your own. Write some music. Enjoy your weekend, even though it's only Tuesday. But yeah, you guys all have a great day. I'll see you guys in the next video. Ciao.